Thank you for everyone for joining the webinar on time here. I'm just looking at the attendees joining. We have several that are coming in on time as well, so we're going to allow for a few more moments for them to sign on in, and then we're going to get started with the presentation. So thank you for your patience, and we'll begin in a few moments. Okay, welcome everybody. My name is TJ Willits, and I'm going to be the moderator for today's webinar for our Anaerobic Operator webinar series. Today's webinar is entitled Pre-Treatment Strategies to Optimize Anaerobic Digestion. Before we get into our presentation, I just want to let you know that you should be hearing me now, as the slide says, and there's two options for audio. Either you could log in using the computer and listen to the presentation on your speakers, or also you could opt for a phone call-in and listen through your phone. Either or will work just as fine. The webinar is being recorded and will be distributed to anyone in attendance or missed the webinar after the presentation tomorrow. Lastly, if you would like to ask questions, feel free to do so during the entire time. At the end of the presentation, we have some allotted time for our panelists to answer those questions. So feel free to enter them as they come into your mind, and then we'll try to get to as many of those questions after the main presentation. Some other things, if you would like a participation certificate, feel free to fill in the survey following the webinar, fill that out and request one, and we'll make sure one gets sent to you via email. And also, please remember to take the survey, and also feel free to offer some suggestions for future content ideas for these webinars. And before we start our presentation, just to introduce our speakers, you're probably very familiar with them already, but our first speaker will be Jill Jordan, who is a senior process specialist with Veolia Water Technologies. Jill has over 35 experience in anaerobic treatment for a variety of industrial wastewaters and a variety of systems, from UASB to EGSB, CSTR, and anaerobic membrane reactors. So the last fun fact of Miss Jordan is that she actually started up the first UASB system in the United States. So she's very experienced and has a lot of good information to share with us today. Our second panelist for today is Timur Denive. He is the manager for our process engineering team at Veolia Water Technologies, and he is obtained a bachelor's and master's in environmental engineering and is currently working on his PhD in the same field. Timur brings over 10 years of continued experience on industrial and municipal wastewater treatment with an emphasis on biological process. Without further ado, I'll introduce our first panelist for today, Ms. Jill Jordan. Jill.
Hi, everyone. Thanks for joining us. Before we start, I want to review a little bit about what we discussed in our last webinar, which was biogas, how to handle it, clean it, and valorize it. And if you don't remember or weren't there, TJ will be glad to tell you how to get that, and you can go watch it in its entirety. But we talked about cleaning biogas, and when we said cleaning, we really were emphasizing the removal of hydrogen sulfide and water. And unless you wanted to get the gas super clean, in which case you had to get rid of the siloxanes and the carbon dioxide in the gas also. And we discussed the four main ways of cleaning gas, which was mechanically, chemically, biologically, or physically. And the big thing is how you're going to use the gas once you've cleaned it. The easiest way, and what was mostly done here in the United States, is to feed it back into a production facility's boiler or in a local boiler at the wastewater treatment plant to heat the wastewater. More and more we're seeing combined heat and power units where the biogas is used to generate heat required by the system and power so you can run your plant with the gas you're generating. There's also dryers that it can be used in, turbines, fuel cells and pipeline injection and CNG. The last three, the fuel cell, pipeline injection, and CNG, actually require very, very clean gas. So you need to go down to that, getting your siloxanes and CO2 out for those. So it's a bit more challenging. But that's, if you're interested in that, again, all of our former webinars are available if you're interested. In today's webinar, we're going to talk about pretreatment strategies to optimize anaerobic digestion. And we really want to optimize the digestion process in high-rate anaerobic wastewater reactors. Those are our UASB and EGSB type granular-based systems. And why is it necessary to pre-treat wastewater? That's the first thing we're going to talk about. And then the second thing is, how do you pre-treat it? So the purpose of pretreatment is to mechanically, physically, chemically, to prepare the wastewater for entrance into the anaerobic treatment system, or specifically the reactor. One of the main things is you want to protect downstream equipment. So all of the equipment in the wastewater treatment plant. You want to protect the pumps. You want to protect the piping. You want to protect the bacteria that's in the reactor. You want to keep things out of the reactor that aren't digestible, that can build up in the reactor. You don't want a bunch of plastic bags in your reactor. You don't want pieces of plastic. You don't want 2x4s in there. They're not even the 2x4 would be digestible to an extent, but you don't want them in your reactor. That's not what UASB and EGSB reactors are designed for. UASB and EGSB type reactors are designed to treat soluble COD, that is, materials that are dissolved in the wastewater. So if there's something in your wastewater stream that's not soluble, we want it out of there. Sometimes wastewater streams contain materials that can be harmful to anaerobic process. One of the big things that can be harmful, although probably mostly biodegradable, is fats, oils, and grease. We don't want them in an anaerobic high-rate system because they can cause the bacteria to float out of the system. Fats float on water. They also can cover the granules, which reduces that activity of the biomass, which is not a good thing. Although some fats, oils, and greases can be digested, it's not going to happen in a time frame that's allowable that we see in UASB and EGSB systems. Another reason for another way to pre-treat wastewater is to equalize the wastewater. We all know that in production facilities, in the food and bev industry, pulp and paper industry, the wastewater doesn't come down from the plant at an even 100 gallons per minute, 24 hours a day, 7 days a week. It varies all over the place. Therefore, it's a good thing to equalize that out. It's better for the system if it can be fed in a stable manner, a stable, steady manner. Let's put it that way. Feeding the same thing 24/7, 365 would be the best thing to do. So equalization is a big thing that we look for these days. So what's not digestible? Solids. You might say, well, I have some cheese curds, or I have some spent grain. They're biodegradable. Well, they might be biodegradable, but first of all, I don't want them in the reactor because they're not going to digest in the time that they can be in the reactor. If you remember or think about your compost pile in your house, it takes months to break down that leaf that you put in there. So the wastewater in your UASB or EGSB reactor is in there less than a day. So those solids wouldn't be in their system long enough to break down. And if they get caught in the sludge bed, they're going to take up space that would be better used by anaerobic bacteria. So we don't want them in there. There's also things that are not biodegradable, like sand and gravel, that would build up in the reactor that you don't want in there. So you want those removed also. Other things, like I say, that are not digestible are large organic particles for a number of reasons in the UASB and EGSB systems, although sometimes they can be digested in mid to low rate systems. A CSTR reactor, you could allow more organic particles in because they have the ability to stay in the system longer. So even in those lower rate systems, you would still want to get out large particles. Again, the 2x4s, the bottle caps, the pieces of glass, the labels. You don't want those in your system, so they would still need to be removed. And back to FOGs, they can upset the high rate systems because, again, they can coat the system. They can coat the system. Yes, they can coat the system, as you can see in that pipe, which is a bad thing. But they coat the granules and they float out and reduce the biomass activity. Although plant and animal FOG is digestible, again, it's not in there long enough to be digested because fats are very complex molecules and they take a long time to break down. There's also the question of what type of FOGs. They're not only the types that are degradable, but if you have hydrocarbons, if you have gasoline, if you have bunker C heating oil, if you have diesel fuel, they're not digestible by the bacteria in your reactors, and they would actually be toxic to the system. So you want those removed from the system. So Timur's going to take over now, and he's going to tell you all about how to determine what type of equipment and processes are available to remove these solids, remove the FOGs, equalize things out. And he's going to take over. Timur.
Thank you, Jill. Thank you very much. Yes, so I'll try to concentrate on the separation systems and separation principles based on the type of solids that we want to remove. Jill just outlined for you in very great detail what kind of solids we want to keep out of the system, or what kind of materials we want to keep out of the system, and the reasons why we want to keep them out. So now we will be diving a little bit more into how we're going to do it from the process perspective. We always like to understand what is that we're removing. Now we know what we don't want, but we also want to quantify and qualify what we don't want. Usually we talk about solids, we talk about total suspended solids, but the total suspended solids is a blanket term. And it's also useful to understand the size distribution of the total suspended solids that we're talking about. And we're talking about the quantity of wastewater treated, but we also want to take about spatial and temporal distribution of the quantity of the water that comes in, especially when we're talking about the equalization. And those factors are all going to be factored in the pretreatment schematic. So what kind of wastewater we have, what is the consistency and the constituents in the wastewater, and how are they distributed in time. And as Jill highlighted, today we will be mostly concentrating on the high rate systems, because the high rate systems are more sensitive to the type of solids that we were describing as compared to the systems that utilize more of a bulk approach to the treatment. So we want as little solids as possible, and knowing that the quality of the effluent that we want as little solids on the effluent, so we want very little solids on the influent as well to the systems. Just to organize our discussion, I will be talking about two main approaches to the solid separation. First approach is the mechanical. So it's the approach that only requires the mechanical forces to separate the solids. And the second is when we're applying the physical chemical principles, so the help and the aid of the chemistry to separate the solids as well. Obviously, all of them have some mechanical features, but in one case, we're talking about gross mechanical separation, and in the second case, we're talking about more of an addition of chemicals and utilizing the forces of gravity and buoyancy. So starting from the mechanical separation, the best example to start with is always your basket strainer. Everyone is very familiar with them, and they're a great example of we're talking about mechanical barrier for the solids. So we're talking about coarse solids that we don't want in our piping and we don't want on our equipment, especially moving parts equipment like centrifugal pumps, for example. So the basket strainer is, as the name implies, is a strainer that's within the basket. So we have a certain size opening that is put inside of the expansion in the pipe, and all we're doing, we're monitoring the differential pressure across the system to make sure it's not clogged. And when it is clogged, we take it out and we remove the gross solids. So it's mechanical and manual. Similar principles, as we can see on the other slide, could be applied in a little bit bigger settings where we have screens that are not just, next slide please, screens that are larger in size, open flow, and could manually be cleaned without interrupting the flow, because in a basket strainer we need to isolate it, take out the basket, and when we have larger flows that becomes counterproductive. So in this cases we're talking about bar screens and the chain driven bar screens, in which cases we have mechanical barrier with the openings of anywhere from 1 millimeter and higher. Usually our sweet spot is 1 to 3 millimeters in opening, and they're preventing coarse materials to move forward. So as we move to the next slide, we see that there are some applications where we're automating the removing of the solids and the cleaning of the screens at the same time. So these types of separation devices do not require as much maintenance, and we're talking about static and rotary screens. In the case of the slide heel static screens, we're applying the water flow against the mechanical barrier, and we're using gravity forces to let the coarse material slide in the hopper, so the treated water proceeds forward and the coarse separated material is accumulating within the hopper. And in cases of the rotary screens, the flow is applied from the inside to the outside of the screen that is rotated, and the scrapers scrape off the solids. So the pictures are worth 100 words or 1,000 words, whatever count you like. And you can clearly see that in a side heel screen, the solids tend to fall down, and in a rotary screen, you can see the scraper on the right corner of the rotary screen that scrapes off the solids as the water is being treated. Moving on from the coarse solids, now we will be talking about solids that are still fine, and they're so fine that applying coarse screens is not going to be practical, but they're also heavy, and they're heavy enough to be easily separated with gravity. And usually in these cases, we're talking about grit. So we're talking about silt and sand particles that are heavy enough that they would settle quickly enough that they're the portion of the solid that would settle quickly enough. So if we take a jar of your wastewater and without applying any chemistry, we just stir the jar up, and the first solids usually that we see go to the bottom within the first couple of seconds are the silt and sand. So just to go over the pictures, and we're talking about the three main types of the grit removal systems. We're talking about aerated chamber, horizontal flow, and the vortex grit removal. Basically what we're saying here is an aerated chamber, we're applying a gentle aeration that keeps most of the things in suspension due to the agitation forces of the aeration, but not enough but we're not applying enough force for the heavy particles to be separated. Similarly, in the horizontal flow, we're basically designing the length of the horizontal flow system so that the sand particle that is entering in the top left corner of the chamber ends up in the bottom right corner of the chamber before water comes out. And they're usually very short, very small systems comparatively because we want to utilize as very little time and separate as grid solids. In the vortex systems, we rely on the centrifugal forces, so we apply a gentle centrifugal force that will push away the heavy solids to the sides while the lighter solids and the water flow continue flowing forward, and we accumulate the heavy solids on the bottom. Next slide, please. Now, while what you're looking at mechanically looks very similar, we will start talking about the physical-chemical separation principles. So now once we remove heavier coarse solids and we remove the grid, we might want to remove lighter particles that are small in size and do not tend to settle quickly, but if we provide them enough help to settle, we will be able to remove them by the forces of gravity or buoyancy. So in those cases, we usually apply chemical pretreatment, such as cationic and anionic polymers or coagulants, or the combination of coagulants and flocculants. And those lighter solids start to agglomerate in larger particles. And once they form larger particles, we can apply similar principles as we were applying to the grid removal, and those are gravity precipitation, except in slightly larger vessels. I'd like to spend a little bit of time on the bottom right picture where you see the lamella plate clarifiers. Basically, what we're trying to accomplish is in a smaller footprint, we're trying to create the conditions of the laminar flow. And the laminar flow is a steady flow without turbulence and agitation present, in order to separate now larger conglomerated particles that tend to be biological in nature and remove them by gravity. But the gravity is not the only force we can apply to the agglomerated lighter particles. We can also rely on the forces of buoyancy. And even in the gravity separators, we would always see what we call a skim layer on the top of the particles that just naturally tend to accumulate on the top. In a lot of cases in the lighter industries, we see a lot of fats, oils, and grease tending to float to the top. So with the addition of chemistry, we sometimes apply the technology that is called the dissolved air flotation, where we basically introduce effervescence bubbles. Same principle as you opening your soda bottle, where after a compressed air is being introduced in the water, and then water is released into atmospheric condition, we form a lot of small bubbles that collect and that aid the buoyancy forces of floatable materials that have been agglomerated together using chemistry, and collecting them on the top and then removing them as a skim layer as the treated water proceeds forward. Next slide, please. So now that we have pre-treated the water for solids, we might want to consider treating water for the pH and the flow equalization. So what we mean by this is, next slide please, in a lot of facilities, if we are looking at the flow coming down, depending on what kind of processes go on, we might not see steady pH conditions, especially if we have different CIP cleaning cycles. We will see the pH swing in some facilities from pH of 2 to pH of 14. So in those cases, we might want to equalize the pH closer to neutral prior to treatment for multiple reasons. One of the reasons for treatment of solids we would like to neutralize pH close to neutral because coagulants and polymers do tend to operate much better at close to neutral conditions. So applying some volumetric equalization of the pH, where we combine streams at different pHs that would self-neutralize, or we provide neutralization system where we have an expansion in line where we can add additional chemistry to neutralize pH. It would aid with the processes downstream, be it the solid separation or the biological process. Next slide, please. And now we're talking, now that we mentioned the pH equalization, a larger challenge for all of the facilities is equalizing the flow. So in the facilities, we never, as Jill mentioned, we never see a steady flow. So let's look at the graph that we're talking about. And this is probably a graph most of you are familiar with, where the facility discharge is not necessarily a steady average flow that if you take all the data points during the day from your lift station would average at a certain flow rate. You see the peaks and you see the dips in the flow throughout the 24-hour period, or let's say 12-hour period. So for us, in order to equalize the flow going into the system, we look at the distribution of those peaks and we say, well, if we apply a volumetric equalization of the certain time, we will be able to dampen out the low points and the high points in the flow and able to provide a steady volumetric flow to the downstream processes that do rely on steady volumetric flow without interruption in service. So how much is required would be directly proportional to the swings in the flows that we see within the system. Short time swings or the prolonged swings in the system will be equalized. But we also want to equalize the load to the system, because not all streams coming down will have the similar COD, COD is the organic load to the system. So we want to make sure we provide enough dampening, volumetric dampening, not to just equalize the volumetric flows, but also equalize the flows from the organic perspective. One more thing, and the concept I'd like to introduce here is the concept of pre-acidification for the high-rate systems. High-rate systems tend to operate much better if we separate the process of acidification. And if some of you have been in previous webinars before, you know the complexity of the anaerobic degradation of the organic material. So the first step of pre-acidification, if we can separate it and do it in the equalization tank and acidify the wastewater prior to going into the further treatment in the methanogenic reactor, we tend to see better granulation and better COD removal going forward. And there is a formula for pre-acidification, but basically what we want is certain amount of time for the biological process to start occurring in the system, so the COD that we have is converted into volatile fatty acids and acidified prior to further treatment downstream. Next slide, please. The calamity tanks is what I've been hearing more and more, and I really like the concept, and I'm glad, even though it's a very old concept, I see a resurgence of it, and I like to talk about it a little bit more. And I think the resurgence comes with the ability to slightly automate the process. In a lot of facilities, what we see is a fairly even distribution of loads throughout the week. But in most of the facilities in the light industries, what we see is that at least once a week, and maybe for a couple hours a day, we see a flow, or rather a slug of the flow, and that usually is associated with CIPing, large fermentation, or the process vessels. That is so much higher in COD that if we just apply the simple average rule, it will substantially skew the COD load into our downstream process, because for those 2 hours, or let's say 2 hours, or for that specific day of the week, the COD is so much higher than the rest of the average. And in those cases, most of the time it becomes really hard to average the load. And then the equipment does not become as effective. So what we introduce a calamity vessel. A calamity vessel sized for that period of time, where you can divert that flow into a calamity vessel so it does not skew your loading into the system so much so that it renders the downstream processes ineffective. And what happens with the calamity vessel is that extra load that is much, much higher than the average is slowly blended into the forward flow of the system and evenly distributed across the rest of the time, so it does not affect the average of the system as much. And we've been seeing the researchers of calamity vessels because we can now automate the process using online TSS or TOC, the total organic carbon measurements. And that substantially aids with the processes downstream and equalizes the flow. So in summary, we went over the solids removal and the removal of non-digestible, harmful materials, grit and FOG. We talked about equalization of flows, loads, and the pH control, and the prevention of the calamity prevention with the diversion tank, which allows us to pre-treat the wastewater prior to anaerobic digestion for the optimal performance of the downstream high rate anaerobic system, and adjust the wastewater so that it is acceptable for the optimal performance of anaerobic bugs. And this concludes our seminar, and I think TJ, back to you.
Thanks, Timur, and thanks, Jill. Just want to remind everyone to go ahead and enter your questions. On the right-hand side there, we have some time left over. We received at least one question so far, but if you'd like to learn a little bit more on this topic, go ahead and enter that into the question panel on the side of the screen. Just want to let everyone know as well that our next webinar is scheduled for mid-September. We're going to take a break over the summer, but we would like to make sure that you guys look out for those email updates in August or September to sign up for that webinar as well. Also, in the survey, please remember to take that survey, provide us some feedback about today's presentation. Also, if there's something specific to your site, we collect ideas from the people who attend our webinars to help us formulate what the future topics will be. So go ahead and enter your feedback there, and we'll analyze it. And if there's enough interest, we'll do a webinar on that topic. Okay, we have one question in queue right now, and it has to do with the max variation of loading. You talked about it being a perfect scenario to load evenly 24 hours a day, but what is the max variation to load within an hour or a few hours or within a day? Can you comment on that?
I'm going to say there is no max, really. It depends on so many other things. Typically, I don't like to see more than a 25% plus or minus the average over a day. That's one of the reasons we like the idea of the calamity tank, because if you have a big dump that comes down in 5 minutes, you could easily have to treat 100 times your average daily load for 5 minutes, which the bacteria probably aren't going to like. So I'm going to say we like to keep the change in loading plus or minus 25% of the average over a day.
Yeah, the standard deviation in that case is if we can dampen it to less than the half of the average value of the standard deviation, then it's much easier to process the flow. And I completely agree with Jill on the calamity. We see sometimes not just 1,000 time increase in a certain parameter with a dump for 2 hours. And it's just not just anaerobic system. I mean, if there is a dump of FOG, your average FOG is 1,000, and then it comes in at 10,000 slug for a couple minutes, your DAF chemistry is going to go off. A lot of processes are going to be interrupted.
Okay, another question we have is related to the calamity tank. Is it possible for a system without a calamity tank to be retrofitted with one? And sort of a related question is, how can you automate that process to monitor and make sure if there would be a catastrophic event, when someone might not be operating the plant, what can you do to prevent it from happening and damaging equipment downstream and off hours?
Very, very good question. And of course, you can retrofit a system to employ a calamity tank. In fact, most of our most recent designs include that, and it's very easy. As long as you have the room and the money, we can put them in. And what we do is we usually monitor the influence for total organic carbon and pH, and have the computer program automatically divert to the calamity tank based on an out-of-spec total organic carbon number and or pH number. So we can divert for either of those two reasons. And those work 24 hours a day, 7 days a week. We've been, yes, Timur's just telling me we could also use turbidity also to look at the an extreme case of a lot of solids coming down in the process. But we've been using a total organic carbon meter to do this, and it's been working quite well at a number of our facilities now. But that's how it works. It's very easy. Total organic carbon measurement in, calamity tank in, some software in your program, and it's all done.
Okay, another question would be is what kind of analysis would need to be done with variations within the wastewater to decide if you would need to employ some type of technology upstream of the reactor? I guess the question would be is what kind of testing should be done on a regular basis, and then when should they give a specialist a call to consider some pretreatment options if they don't have any already?
So here we're talking about the concept of the composite sample and the grab sample. So the composite sample is usually a sample that is accumulated over a certain period of time. Usually that period of time is the period of time that you would be planning to equalize the flow for. So if you're planning to have an equalization vessel that is timed at 12 hours, you probably want to collect samples for composite samples over a 12-hour period. But the basic idea here is, if you're just starting to make a decision, implementing a good testing program consistent of not just composite but also grab samples is what we usually look for. In cases like this, we either work with our clients or we recommend that our clients, first of all, look at their flow distribution. So let's say you have a single lift station, hopefully, in your facility where all of the wastewater comes in before it's getting either treated, sending to treatment, or sent to the city. So it's very important to see the flow distribution in that lift station. And then at the times when the flow occurs, it would be prudent to collect the samples or design the treatment schematic, the sampling schematic. So you collect the samples at the time that the flow occurs, and you test them for the main parameters. We're not talking about it a lot. Usually all we look for is TSS, FOG, and COD, and maybe the soluble components. And in that way, you see the flow and the load distribution in your facility, and it's going to be so much easier to make decisions about the calamity and equalization and the further treatment that you want to implement.
A lot of times these, like Timur talked about the composite samplers, but these composite samplers can be set up to take a sample like once every hour for 24 hours, or once every so many gallons over a 24-hour period, and separate samples. So, and to analyze each one of those samples over the time period gives you a good idea of how the flow and loads vary over the day. And analyzing those is what determines whether you're going to need how much upstream pretreatment and what that might need to be.
Okay, well that concludes our question and answer session. If you have any additional questions, Jill Jordan's contact information is on the screen. Also, you can feel free to contact myself if you have any additional questions, or if you'd like to have access to some of the other previous webinars, we'll be happy to make sure you have access to those. We just want to wish everyone a great and safe summer, and we'll look forward to hosting you at a future webinar in the fall. Thank you.
Thank you, everyone.